Hello everyone, my name is Qingsong Chen. I'm a postgraduate from Wuhan University. It is a pleasure to present our recent work on the EAI conference. And the topic is a security-enhanced key management service for ARM Pointer Authentication. Here begins. According to Google's report, memory corruption bugs generally accounted for more than 65% of high-end critical security bugs in Chrome and Android, such as stack or heap buffer overflow, use after free and double free. There are two types of attacks based on it, code injection and code reuse. And code injection attacks can be mitigated by the stack canary, DP, and ASLR, so the code reuse attacks generally become a major threat and the main pattern of hacking the software and system security. The code reuse technique, like return-oriented programming, allows the attacker to reuse the existing code fragments in memory and manipulate them to launch powerful attacks in order to defend against such attack. The control flow integrity was proposed to sign the pointers, like return address and function address. However, software implementation of CFI are limited by the high performance overhead, and hardware-assisted ones are requiring the underlying processor architecture changes. Therefore, ARM introduced pointer authentication in ARM V8.3 extension, utilizing dedicated instructions and system registers to sign and authenticate pointers efficiently. But PA is still vulnerable to certain attacks, and it motivates us to do this work. Before elaborating our work, some background knowledge is necessary. Firstly, we need to know the ARM V8-A exception levels. As shown in the figure, the exception levels are referred as EL0 to EL3. EL0 is the least privileged one, typically used for applications, and EL1 is for the operating system, while the EL0 and EL1 is available in both the non-secure world and the secure world. The EL3 is the most privileged one that only resides in the secure world and is reserved by the low-level firmware. The current exception level can only be switched when the processor takes or returns from an exception, and the SMC instruction can cause an exception to EL3 and the SVC instruction to EL1. There are two types of privilege relevant to the exception levels. One is memory privilege controlled by memory management unit and isolated by the Qingsong address-based controller in hardware. Another is the privilege of accessing processor resources, like system registers. Generally, the name of the system register indicates the lowest exception levels required by a successful access. For example, the register TTBR0 EL1 holds a base address over translation table of applications at EL0, which requires privilege of EL1 at least. Then we need to know how ARM pointer authentication works. PA provides instructions to calculate and verify the pointer authentication codes for pointers. The figure shows how PAC instruction works. It calculates a PAC over a 64-bit virtual address with unused bytes, a 64-bit modifier, as a customized context, and a 128-bit secret PAK stored in system registers. Then it uses a hash function to yield a PAC and embedded it into the high bits of the original address. There are 5 types of PAKs. IA and IB are for the code pointer, D and DB are for the data pointer, and GA is for the general use. Take the PACIA XD XN instruction as an example. The original pointer is kept in the register XD, and the modifier kept in the register XN, and IAK is composed of 2 system registers, API K high EL1 and API K low EL1. After calculations, the signed pointer is returned by the register XN because the memory tag extension introduced by ARM V8.5 also utilizes the high bits. The PAC size may be limited by it. Now we will talk about the attacks on PA. The first possible attack is PAC brute forcing. This is because the PA keys of a process are constant and shared by all the threads in a single address space. The key will only be reset until the process is killed. Additionally, PC is limited in length. When the V size is 48 bits and MT enabled, the PC size is merely 7 bits, and when PC authentication fails, it returns an invalid pointer and will not immediately trigger an exception. So the key will not be reset. Hence, we can do a calculation and know that a correct guess won't take much effort. When the PC is 16 bits and no key reset, about 30,000 attempts are enough. The second attack is pointer substitution. Similarly, this is because the PA keys are constant and the modifier is simple and non-unique. It can be either static or dynamic. On the one hand, reverse engineering could reveal the static modifier, and the threat model of PA assumes that the attacker could read and write to almost the entire address space, restricted only by DEP, which also exposes the value to the attacker. On the other hand, take the stack pointer as an example. It is not required to be unique for function 1. Therefore, attackers could reuse the assigned pointer in function 2 when it executes with the same stack pointer as shown on the right. And when the attacker can control the modifier 2, making it equals to modifier 1, then the attacker could reuse the return address of function 1 and construct a loop gadget to hijack the control flow. The last possible attack is cryptanalysis against the default hash function QRMA. We know that the PA keys remains constant throughout its lifetime and are shared by all threads in a single address space. A constant PA key is fragile to cryptanalysis attack based on known PAC values, and the default QRMA algorithm used by PA can be attacked. Researchers have proposed several methods such as meet in the middle and impossible differential attacks. At the same time, shared keys expand the search space for attackers to find a usable signing and authentication gadget. Thus, a sophisticated attacker could observe and collect adequate pairs of the original pointer and the assigned ones to attempt such attacks. Some papers show that the attacker only needs to choose a set less than 70,000 plain text to recover the key. Now we will talk about the threat model in this work. We consider a powerful attacker who has the capability to read and write almost the entire address space, constrained only by DEP. He or she can read any program memory, write to no-code segments, and cannot tamper existing instructions or load malicious shared libraries, and cannot read or write the system registers directly, especially the PAK's registers. We do make some assumptions about the system as well. The firmware and secure monitor in EL3 is trusted. The TZASC is configured correctly to separate the physical memory space. The kernel boot-up process is trusted, since the bootloader reset in EL3 can easily verify their cryptographic hash of the binary, and the random number generation has expected random entropy. Before illustrating our work in detail, we need to address security challenges arising from the contradiction between the existing management pattern and the thread mode. The Linux kernel stores PA keys in thread struct to support each process signing and authentication pointers correctly, leading that the keys can be leaked or informed. In order to maintain the confidentiality of PA keys, we must provide a distinct solution to make use of PA with no keys residing in the kernel memory. The PA keys of a process are constant and shared by threads, and that makes the program suffer PAC brute forcing or pointer substitution attacks. So we need a scheme to provide dynamic or variable PA keys for programs. The diversity means that a pointer cannot be forged or used by attackers to reliably replace a different pointer. Currently, since the PA key remains constant, the diversity mainly relies on the modifiers, but the modifier is simple and non-unique. Our scheme needs to provide distinct keys for different contexts, or for the same context in a different time. So we propose the Pointer Authentication Key Management Service to provide PA keys for the kernel and user space applications, which ensures the confidentiality, variability, and the diversity of PA keys. Our idea is simple, and to make the PA keys changeable, we use a variable to generate PA keys for EO1 and EO0, namely GN, on behalf of the generation of PA keys. And PKMS in EO3 initializes and holds the master keys and GN confidentially, prevents other exception levels from direct read and write. At the same time, PKMS generates PA keys for EO1 and EO0 in system registers, and does not bank them to the kernel memory, ensuring the confidentiality of PA keys. And the kernel in the middle plays two roles on the whole. For one thing, the kernel can use SMC instructions to call PKMS for signing and authentication pointers in kernel. And for another, the kernel plays a role of a bridge between the PKMS and the user space applications. And the proxy also checks and records the PSA authentication failures for EO0 applications. While invoking the PKMS, we can pass some unique context parameters to ensure rich diversity of PA keys, resulting that different kernel threads have distinct keys. Optional parameters are the values of the register TTBR1 EO1 and TBIDR EO1. The former holds the base address of the translation table of kernel address space, which can be used to separate keys of the kernel from the user space applications, and the latter store thread identifying information, and can be used to produce distinguishable PA keys for kernel threads. And further, function-level parameters can be passed to produce fine-grained PA keys for each function. Due to that, SMC instruction is undefined in EO0. The application in EO0 uses SVC instructions to call kernel proxy for signing and authentication pointers. A local GN will be returned by PKMS and can be stored on the stack in order to correctly authenticate signed pointers later, because GN in EO3 is variable throughout the system. Similarly, the register TTBR0 EO1 and TBIDR EO0 can be used as context parameters to produce PA keys associated with specific user space applications. Now we will detail the key generation algorithm. After the firmware accomplishes the necessary architecture and platform initialization, PKMS initializes 5 master keys and 1 GN with random value output time, and at the same time set up the EO3 physical timer to update GN with some strategy. When the PKMS is invoked at runtime, it selects suitable context parameters for EO1 and EO0 according to the service's identifier. Then it goes to the signing and authenticating key generation processes separately. In the signing procedure, PKMS applies such context parameters and global GN to generate PA keys using some specific algorithm. In this paper, we choose QRMA for the reason that the PAC instructions have provided an efficient implementation. Then, if the task can be preempted, PKMS uses PAC instructions to assign the pointer directly, or else leave PAC calculation to the context, and return the local GN to be utilized in the authenticating procedure. As we can see in the authenticating procedure, PKMS applies the input local GN to generate the authenticated keys, and use AUT instruction to verify the signed pointer. Based on the ARM trusted firmware and LLVM compiler toolchain, we implement a prototype of PKMS, and we simulated it on the ARM fixed virtual platform. We modified the firmware code to configure the generic interrupt controller and trust zone controller in order to isolate the PKMS in EO3, and set up a register SCTLR EO3 to enable PA in EO3. We also set the EO3 physical timer control register, that is the CNTPS CTL EO1, set the enable bit to 1 and the IMASC bit to 0. When the timer fires, an interrupt signal is set to the interrupt handler. Then we can update GN in the interrupt handler. The LLVM instrumentation example code listing are like this. The left is used for the kernel and the right for the user space applications. We can see that the kernel uses SMC instruction to call PKMS, and the application uses SVC instead. and the non-preemptive kernel can use PAC AUT instructions directly to protect the integrity of the kernel pointers. However, the application should rely on the kernel proxy to sign and authenticate pointers to avoid mistakes. In addition, the application should utilize the BR instruction to return to the location pointed by the register X0, which holds the authenticate return address. The security problems of existing PA-based schemes are stemmed in the immutability of each process's PA keys managed by the kernel. PA mask, however, can provide different keys to the same process or even the same function context in different time. Therefore, PA keys are distinct between context, and the PAC authentication fields can be checked in kernel proxy, preventing the PAC brute forcing attack. And when generates the PA keys, the rich and unique context parameters make it impossible to substitute pointers in different contexts. We also evaluated how many CPU cycles needed by PAC instruction and PAKMS to calculate PACs. The result is shown in Table 1, so that we can set the timer properly to update GN in order to prevent it calculating too much PACs based on the same key, which can mitigate the cryptanalysis attack. We choose MBench to evaluate the performance overhead of PAKMS for the reason that MBench is designed to measure CPU and memory subsistence performance with real-world algorithms, and it's easy to be migrated to new processors or operating systems quickly. We set up 3 sets of evaluations. The baseline uses unmodified firmware, kernel, and MBench, and the PAKMS-K modifies the firmware and kernel. The PAKMS-KN modifies all of them. The result shows that the overhead of PAKMS is reasonable and acceptable. Even the worst case, IDEA, this is because all the operations in IDEA needs to call its internal functions separately, and it can reduce the overhead by optimizing the algorithm with less function calls inside. In conclusion, in this work, we proposed a novel scheme providing security-enhanced key management service of PA, which could dynamically generate distinct keys for both the kernel and user space applications. And our evaluation shows that it introduced a reasonable and acceptable performance overhead while providing better security guarantee. In future, we will evaluate the performance of PAKMS comprehensively on the PA-capable hardware and support more signing and authenticating patterns. So this is the end of my topic. Thanks for your attention and listening.
Hello everyone, I'm Hongwei Luo from Beijing University of Posts and Telecommunications. Today it's my great honor to share my research about the three-factor authentication. The topic of my paper is privacy-preserving ECC-based three-factor authentication protocol for smart remote vehicle control system. The outline of my presentation is introduction, review of Chatterjee et al.'s scheme, the proposed protocol, performance evaluation, and conclusion. At the very beginning, let me introduce our paper. In the past few decades, with the upgrading of automobile control system, the human-vehicle interaction mode has been constantly changing. In the beginning, people used traditional mechanical car key to open the door and start the car. Later, car manufacturers embedded electronic control devices in the car, which enables people to control the doors remotely by pressing the button on radio car keys. The remote control function of radio car keys is mainly realized by the embedded RFID chip in the communication process between the radio key and the car electronic control device. Generally, a symmetric encryption algorithm such as AES is used to protect the confidentiality of the message. But some works show these radio car keys are subject to relay attacks. The attacker can actively or passively control the car from a long distance through the relay device. What's more, when the long-term symmetric secret key stored in the radio key is acquired, the vehicle control right will easily be changed. Furthermore, with the development of Internet of Things and the Internet of Vehicles, smart remote vehicle control SRVC systems are gradually appearing in much more cars. This charging system allows people to use smart devices to control the vehicle. Users can control doors, windows, start and turn off the engine, and read the real-time data of their vehicles from far away. The communication model of SRVC system contains three partners. They are smart device, car enterprise server, and in-car smart terminal. Firstly, the user and the vehicle register themselves with the enterprise server. Then the user and the vehicle negotiate a session key through the enterprise server. Finally, the user and the vehicle use the session key for point-to-point control message transmission. This sounds like traditional IoT communication model. However, there are some differences between two models. The enterprise server and the in-car smart terminals has strong computing power and stable network connection. So more complex computing tasks are acceptable. Comparing to the latency of a mobile network, the key agreement phase of SRVC system is not sensitive to time cost. The third, the security and privacy protection capabilities of SRVC protocols are more important for vehicle control is closely related to human life safety. Here is the adversary model. We suppose that the adversary can intercept, modify, delete, and replay all messages transmitted via insecure public channels in the protocol. The adversary may have the ability to obtain the data stored in the smart card or in the car enterprise servers. Besides, the insider attack can also perform an insider attack to obtain confidential information from the enterprise database. There are a few schemes related to SRVC system. After studying many protocols, we found that the communication model in Chatterjee et al.'s scheme is similar to us. Unfortunately, there are some security weaknesses. The figures show the login and authentication phase of Chatterjee's et al. Scheme. In this phase, the smart device, the IoT node, and the gateway server authenticate each other over a public channel. We believe that the scheme suffers from user impersonation attack, since the public and private keys are generated in advance. If the adversary is able to obtain any two private keys, he can perform a user impersonation attack, taking DN and DG. For instance, the adversary can easily get DID for it is transmitted in plain text. Then he generates a nonce NI star and compute this, the hash value, and send this strings to the gateway server. When the gateway server receives the message, it checks the validation of the message with this hash value, and obviously the message can pass the check. When the IoT node transmits a message to the adversary, he is able to compute P with dn.kd. Then the adversary selects random R and computes SK and sends R to the IoT node. Finally, a session between the adversary and the IoT node is established. Their scheme also suffers from user tracking attack. In login authentication phase, the smart device sends DID to the gateway server in plain text. Although DID is not directly related to user's identity, it is fixed for specific and not updated with each session. When monitoring the public channel, the adversary can launch a tracking attack with this fixed value. Then he might collect sensitive information related to the user, like user's location, user's traveling routes, and so on. Furthermore, since none of three participants in the scheme checked the freshness of messages and response messages with calculated values, the scheme cannot defend the DOS attack either. The adversary can eavesdrop a message and resend it a large number of times, making the gateway server of IoT node out of service. In order to improve their scheme, we put forward a three-factor authentication scheme for SRVC system based on ECC. It includes three kinds of participants. That is, the user U, the car enterprise server S, and the vehicle smart terminal T. In registration phase, S is responsible for storing and issuing hashed user information to U and T. In login and authentication phase, S is responsible for implement mature authentication and negotiate session key between U and T. The user registration phase is shown in the figure. Let me introduce the detail. Step 1. A user U first gets TID of his car from the automobile enterprise. Then you randomly pick a UID, a random RU, and choose a password PW. You compute this hash value and send parameters UID, hash value, TID via a secure channel. Step 2. Upon receiving UID hash values ID as picks to random numbers IS and RT and announce N0 computes A0, this value, and some other values here, and then S sends CST TID to T. Both two data transmissions are carried out via secure channel. when you receive the smart card, he imprints his biometric data B, computes C1, C2, and replace the hash value in smart cards with C1 and C2. Now smart card contains C1, C2, CUS. The last step upon receive of CST, CID, T computes TID and store this hash value and CST in a secure storage space. Next is the login and authentication phase. Step 1, firstly, you read C1 and C2 and CUS from the smart card with the input of UID, PW, and B. You compute the T1 is equal to C1 inclusive of this hash value. T2 is here, and the next you compute CSC value and check if CST is equal to CST. If they are equal, which means AI is equal to T2. And you select a random DU, which is belonging to ZP, picks a random nonce NI, and computes QU. There are a lot of steps. We don't need a very specific explanation. However, they just finish some computes in the U side and transmit this value to the server S. Upon receiving the login request message 1 from US first check T1, and here is some steps in the server S. And then we can go to here. After some computes in S side, the server S sends these values to the terminal T. Here is the T's computes. If T2 is fresh, compute T4, T5, KST, check this hash value, whether it is equal to V2, and select D2, and finish all these computes, and then transmit this value to the server S, and there are a lot of computes in S that. And here is some other computations. However, there are many computations in these steps, and after this we can go to the performance evaluation. Taking into account the characteristics of the SRVC system, our protocol achieves a higher security at the cost of increasing computational complexity, as is shown in two figures. There are more hash operations, bare hash operations, and ECC point multiplication operations in our protocol. However, mobile smartphones, enterprises, servers, and in-vehicle smart terminals can fully afford these calculations. As a consequence, our scheme achieves a better security performance. According to the figure, our protocol has several security properties and can defend many known attacks. Comparing to 3 other works, ours is the safest. Let me conclude our work to you. We first introduced the smart remote vehicle control systems features, which are similar but also has differences with IoT systems. Then, based on the Yao adversary model, we analyze strategies at all the 3-way ECC-based IoT authentication protocol and demonstrate the limitations in this protocol, such as lack resistance of DOS attack, impersonation attack, and user tracking attack, to give more security for SRVC system. Then we propose a privacy-preserving ECC-based 3-factor authentication for SRVC system. Lastly, security and performance analysis show that our protocol can resist known attacks and has better effectiveness. Yeah, thank you very much for your attention.